Alright, let's go. Number 10. The GW150914 mass mismatch. In late 2015, engineers at the twin LIGO observatories, Hanford in eastern Washington and Livingston in the swampland of Louisiana, were running final calibration tests on their newly upgraded advanced LIGO detectors. The formal observing run had not yet begun. Teams were verifying laser alignment, chasing environmental couplings, sweeping the noise floor for the last stubborn artifacts that had haunted the instrument through a decade of redesign. Nobody expected to catch anything real. Standard stellar evolution, refined across 40 years of textbook consensus, predicted that black holes formed from the collapse of single massive stars in our chemically enriched galactic neighborhood should peak somewhere between 10 and 15 solar masses. Massive stars lose material through fierce, radiation-driven winds. The heavier the star, the more brutally it sheds. By the time the iron core collapses, most of the progenitor's mass has already been blown into interstellar space. On September 14, 2015, at 9 hours 50 minutes and 45 seconds UTC, 3 days before official science mode, a signal swept through both detectors within 7 milliseconds of each other. The waveform was clean, the masses were wrong. In their 2016 paper in Physical Review Letters, BP, Abbott and the LIGO scientific collaboration reported a merger of a 36 solar mass black hole with a 29 solar mass black hole, radiating 3 solar masses of pure energy as gravitational waves in less than half a second. Wind-driven mass loss models were the first casualty. Low metallicity progenitor scenarios were proposed as a rescue. Chemically poor stars lose less material, but population synthesis codes could not manufacture such objects in the observed abundance. Dynamical formation inside dense globular clusters was invoked next. Then primordial black holes seeded in the earliest microseconds of the universe. Each patch required assumptions the data would not confirm. The mass distribution refused to fit any single formation channel. The very first gravitational wave humanity ever measured came from a pair of objects that, according to our best pre-2015 models, should not have existed in that mass range at all. Every theory of how stars die was quietly rewritten. What else did we think we understood about stellar collapse that will not survive the next observing run? The next anomaly did not come with a template at all. Number 9. The unmodeled burst signals. By the third observing run, the LIGO-Virgo collaboration was running 2 parallel search pipelines at all times. The first, called matched filtering, compares incoming data against millions of pre-computed waveform templates, binary black holes, binary neutron stars, neutron star black hole pairs. The second, called coherent wave burst, was designed by Sergei Klemenko and his team at the University of Florida to catch anything the templates would miss. General relativity is exquisitely predictive for 2 compact objects spiraling into each other. The waveform is calculable to more decimal places than any experiment can measure. Any real astrophysical merger should produce a signal that lines up cleanly with one of the pre-computed templates within statistical noise. Occasionally it does not. Coherent wave burst has flagged short-duration transients, millisecond-scale bursts of coherent power appearing simultaneously across geographically separated detectors that carry no matching waveform in the entire template bank. In a series of papers beginning with the LIGO-Virgo all-sky burst search results published in Physical Review D across 2019 through 2022, the collaboration cataloged multiple candidates that survived data quality vetting but could not be identified with any known astrophysical source. Core collapse supernovae were the first proposed explanation, but no coincident supernova was ever found in the sky patches. Magnetar giant flares were tested and ruled out by their expected spectral signatures. Cosmic string cusps were floated as an exotic possibility. So were phase transitions in the early universe, and more radically, unknown compact object populations. Each hypothesis was tested against the observed burst morphology. None matched cleanly. The candidates were quietly filed as unidentified, waiting for a coincident electromagnetic counterpart that never arrived. Somewhere, at a distance we cannot measure, an event released a spasm of space-time distortion violent enough for our detectors to record, and we have no theoretical framework that tells us what produced it. If the source is not a merger, not a supernova, not a magnetar, then what, precisely, is out there ringing space-time like a bell? The next puzzle involves objects that should not be able to form at all. Number 8. The mass gap black holes. For roughly a decade before advanced LIGO switched on, X-ray astronomers had assembled a demographic map of stellar remnants. Farial Ezel of the University of Arizona, working with Dimitrios Saltis, Ramesh Narayan, and Jeffrey McClintock, published a widely cited 2010 paper in the Astrophysical Journal analyzing the mass distribution of black holes in galactic X-ray binaries. Their result was striking. Neutron stars clustered below about 2.2 solar masses. Black holes clustered above roughly 5 solar masses. In between, from 2.5 to 5 solar masses, there was almost nothing. This became known as the lower mass gap, and theorists constructed elaborate supernova models to explain it, invoking rapid convective instabilities that either fell back onto a neutron star or blew apart the star entirely, leaving no remnant in that range. On August 14, 2019, LIGO and Virgo detected a merger between a 23 solar mass black hole and a compact object of 2.59 solar masses, published as GW190814 in the Astrophysical Journal Letters, Volume 896, by Abbott and colleagues in 2020. The secondary sat directly inside the forbidden zone. It could be the heaviest neutron star ever discovered, exceeding the theoretical maximum set by every equation of state consistent with dense nuclear matter. It could be the lightest black hole ever discovered, born from a supernova channel that theory said should not produce anything at all. There is no electromagnetic counterpart to help decide. No tidal deformation signature strong enough to distinguish. Then, in May of 2023, a second event named GW230529 was recorded with another secondary sitting inside the same gap. The rescue attempts were immediate. Perhaps the equation of state of neutron matter is stiffer than nuclear physics predicts. Perhaps the fallback supernova mechanism is more permissive than models allow. Perhaps we are seeing primordial objects. Every proposed fix demanded that some existing theory, previously considered settled, must be wrong. If the mass gap is not a gap, then either the maximum mass of neutron matter is unknown, or an entire class of stellar deaths has been miscategorized. Both possibilities rewrite parts of physics you were taught in undergraduate courses. Which piece of the standard picture do you choose to abandon? The disagreements go deeper, into the very timing of detection. Number 7. The timing residuals between LIGO and Virgo. The sky localization of any gravitational wave event depends on triangulation. Because the wavefront travels at exactly the speed of light, the arrival time difference between geographically separated detectors constrains the direction the wave came from. LIGO Hanford and LIGO Livingston sit approximately 3,000 kilometers apart, giving a maximum light travel time difference of about 10 milliseconds. Adding Virgo, near Cassina in Italy, extends the baseline further. All three sites synchronize their data streams to GPS timing with sub-microsecond precision. In principle, the arrival times of a genuine astrophysical signal should be consistent to a fraction of a millisecond after accounting for signal morphology across detectors. In practice, discrepancies appear. In papers published across 03 and 04 by the LIGO-Virgo-CAGRA collaboration, several detected events showed timing residuals that fell outside expected instrumental uncertainty budgets, forcing analysts to widen sky localization contours dramatically. GW190425, detected while Hanford was offline, produced a localization area of roughly 8,000 square degrees on the sky, a full fifth of the entire celestial sphere. Instrumental clock drift was the first candidate. GPS anomalies were checked and ruled out. Environmental couplings, seismic noise, magnetic field fluctuations, transient temperature shifts in the vacuum enclosures were audited exhaustively. Some residuals were attributed to detector-specific calibration errors that could be corrected post hoc. Others could not. The debate has never fully closed. Either the noise budget contains an unmodeled component that shifts arrival times at the millisecond level, or something in the signal itself is dispersing in a way general relativity does not predict. General relativity forbids gravitational waves from dispersing. All frequencies must travel at exactly the same speed. If they do not, the graviton has mass, and the entire structure of Einstein's theory needs revision. Constraints from Abbott and colleagues in Physical Review Letters have pushed the graviton mass upper bound to extraordinarily low values, but the residuals persist. Every unlocalized event is a patch of sky where something violent occurred, and we cannot point our telescopes at it precisely enough to see what. The orbits themselves carry a signature we did not expect to see. Number 6. The eccentric merger orbits. The prevailing wisdom for stellar mass binary black hole formation, refined across 3 decades by Krzysztof Belginski and collaborators at the Nicolaus Copernicus Astronomical Center in Warsaw, was straightforward. 2 massive stars form in a bound binary. They evolve together through mass transfer, common envelope phases, and eventual supernovae. By the time both cores have collapsed into black holes, gravitational wave emission has spent millions of years circularizing the orbit. Any residual eccentricity is radiated away long before the pair reaches frequencies detectable by LIGO. The waveform at merger should show 0 eccentricity to within measurement precision. On May 21, 2019, LIGO detected GW190521, an 85 solar mass black hole merging with a 66 solar mass companion, producing a 142 solar mass intermediate mass remnant, reported in Physical Review Letters by Abbott and colleagues in 2020. Isabel Romero-Shaw, Paul Lasky, and Eric Thrane at Monash University published follow-up analyses in the Astrophysical Journal Letters, arguing that the signal was consistent with a residual orbital eccentricity of roughly 0.1 at 10 Hz, a value the isolated binary evolution channel cannot produce. Independent groups reanalyzed the data. Some confirmed the eccentricity. Others argued spin precession could mimic the same waveform features. Rasula Gayatri and collaborators reached similar conclusions using different waveform models. Standard field binary evolution was ruled inconsistent. Dynamical capture inside dense globular clusters was proposed as the natural rescue. A second black hole swings past and is gravitationally captured on a highly elliptical orbit, but the required event rate strained cluster population models. Formation inside the accretion disks of active galactic nuclei, where black holes migrate and pair through gas-mediated interactions, became the second candidate. Neither has been confirmed. The distinction matters for cosmological inference, for the assumed formation history of every binary in the LIGO catalog, and for whether the universe manufactures black holes through mechanisms we have not yet identified. If dynamical capture in exotic environments produces a significant fraction of what we detect, the entire statistical framework we use to weigh cosmological parameters from these events is contaminated by a channel we cannot cleanly model. The universe was making these events unnoticed long before our detectors could hear them. Number 5. The stochastic gravitational wave background hints. For 20 years, radio astronomers had been timing an ensemble of millisecond pulsars scattered across the galactic disk. These are neutron stars spinning hundreds of times per second, whose pulse arrival times are so regular they rival atomic clocks. Any gravitational wave passing through the galaxy stretches and compresses the space between Earth and each pulsar, subtly shifting the observed pulse timing. The North American Nanohertz Observatory for Gravitational Waves, known as NanoGrav, had been building a 15-year dataset for exactly this purpose. In June of 2023, in a paper led by Gabriela Agazi and published in the Astrophysical Journal Letters, Volume 951, the collaboration reported evidence for a stochastic background of gravitational waves at nanohertz frequencies, detected through the Hellingsdowns quadrupolar correlation signature between pulsar pairs. The statistical significance sat between 3 and 4 sigma. Independent confirmation arrived within days from the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Chinese Pulsar Timing Array. The interpretation was not straightforward. The prevailing explanation invokes a cosmic population of supermassive black hole binaries, pairs of billion solar mass objects at the centers of merging galaxies, whose collective inspiral produces a low-frequency hum permeating spacetime. The amplitude of the signal, however, ran slightly higher than most SMBH binary population models predicted. Rescue models proliferated. Cosmic string networks left over from early universe phase transitions could reproduce the spectrum. So could inflationary gravitational waves stretch to nanohertz scales by the expansion of the universe. So could primordial black hole binaries, or a first-order phase transition in some dark sector we have never directly observed. Distinguishing these hypotheses will require another decade of timing data. The signal itself is real. Its origin is not agreed upon. If the background is dominated by anything other than supermassive binaries, it means the universe contains structures or processes, cosmic strings, dark sector transitions, primordial remnants, that we have never seen and cannot yet detect any other way. The problem, though, begins inside the instrument itself. Number 4. The glitches that mimic real signals. Both LIGO detectors are subject to a chronic population of instrumental artifacts that produce transient bursts of excess power in the strain data. The classifications are informal but universally used across the collaboration: blip glitches, koi fish, scattered light, tomte, whistle, low-frequency lines. Their morphology varies. Their origins are, in many cases, unresolved. Some come from environmental sources: trucks passing on nearby highways, wind loading on the vacuum tubes, seismic activity from distant earthquakes. Others originate inside the interferometer itself: mirror suspension resonances, laser intensity fluctuations, mode cleaner instabilities. To manage the deluge, the collaboration launched Gravity Spy in 2016, a citizen science project hosted on the Zooniverse platform, led by Michael Zevin, Scott Coughlin, and colleagues from Northwestern University, publishing methodology in classical and quantum gravity. Volunteers around the world classify glitch spectrograms by shape, training machine learning models to auto-flag artifacts. On August 17, 2017, at the moment LIGO Livingston detected the neutron star merger GW170817. A large blip glitch appeared in the same data stream within a second of the merger signal. The glitch was so severe, it had to be manually subtracted before the astrophysical waveform could be recovered. Had the glitch coincided precisely with the merger peak, the detection might never have been confirmed. The disturbing question is not what to do when a glitch appears near a signal. It is how many real signals have been discarded because a glitch appeared exactly on top of them. And, more uncomfortably, how many events already listed in the catalog are glitches sophisticated enough to have passed every vetting stage. The false alarm rate is a statistical construct, not a certainty. Each entry in the confirmed catalog carries a probability of being noise. That probability is small. It is not zero. Somewhere in the LIGO catalog may sit an entry that no astrophysical event ever produced, and no reanalysis will ever prove it. The follow-up observations tell their own uncomfortable story. Number 3. The neutron star merger light curve anomalies. The GW170817 event is arguably the most scrutinized astrophysical observation in human history. Within 11 hours of the gravitational wave detection, ground-based telescopes had localized the optical counterpart AT 2017 GFO in the galaxy NGC 4993, roughly 130 million light-years away. Radio, infrared, optical, ultraviolet, X-ray, and gamma-ray observatories tracked the aftermath for years. Pre-merger kilonova models developed by Brian Metzger at Columbia University and Daniel Kaysen at Berkeley predicted the electromagnetic signature, a rapid ejection of neutron-rich material, followed by R-process nucleosynthesis of heavy elements, producing a bright blue optical component that would fade into a red infrared component over days as heavier lanthanides took over the opacity budget. The observations did not match cleanly. The early blue emission was brighter and lasted longer than most pre-2017 models permitted. The transition to the red component came on a timescale several groups struggled to reproduce. Then, beginning in 2018 and reported in Nature by Kunal Muli, Adam Deller, and colleagues, radio observations revealed apparent superluminal motion in the associated jet, an effect only explicable through a highly relativistic, off-axis structured jet, not the simple cocoon models that had originally been favored. Late-time X-ray brightening continued for years after most models predicted the emission should have faded. The debate between structured jet models, cocoon breakout models, and hybrid scenarios has never fully closed. Each modification required adjusting parameters for jet opening angle, viewing angle, ambient medium density, and ejecta geometry. What was meant to be the definitive test of kilonova theory instead became a chronic reminder that our understanding of how heavy elements are forged and dispersed in violent stellar deaths is incomplete. The gold in your wedding ring may have been produced by an event we still cannot fully describe. If the models cannot reproduce a single well-observed merger, What does that say about the origin of every heavy element on Earth? The signal after the merger carries its own quiet contradictions. Number 2. The Ringdown overtone discrepancies. When two black holes merge, the resulting object is briefly deformed, and it settles into its final Kerr geometry by radiating away the deformation as a spectrum of damped sinusoidal oscillations called quasi-normal modes, or the Ringdown. General relativity, through the no-hair theorem, makes an astonishingly clean prediction. The entire Ringdown spectrum, frequencies and damping times of every overtone, is determined by only two numbers, the final mass and final spin of the remnant. Every overtone must be consistent with those same two numbers. Any deviation is a signature of new physics beyond Einstein. In a 2019 paper in Physical Review Letters, Maximiliano Isi, Will Farr, Matt Giesler, Katerina Chatzianou, and Saul Tucholsky reported an analysis of the GW150914 Ringdown that isolated the fundamental mode and the first overtone separately. They claimed evidence at roughly 3 sigma confidence that both frequencies were consistent with the same final black hole parameters, a successful test of the no-hair theorem. Then, in 2022, Roberto Cotesta, Sylvain Marsat, and Michael Purrer published a reanalysis in Physical Review D, arguing that the overtone detection had been overstated, and that the statistical significance dropped substantially with more conservative noise modeling. A public methodological argument followed. Independent groups have since tested overtone recovery on more recent higher signal-to-noise events like GW200129 and GW230814, with mixed and contested results. The tension is not academic. If the overtone frequencies deviate from Kerr predictions, black holes have hair. They carry additional structure, quantum, exotic or otherwise, beyond mass and spin. The no-hair theorem, one of the most rigorously derived results in classical general relativity, would need revision. If they do not deviate, we have simply not yet reached the precision required to see the deviation. Either general relativity is being confirmed to unprecedented precision, or it is being falsified at a level our current statistics cannot yet resolve. And through all of this, we can only hear a narrow slice. Number 1. The unresolved question of what else is out there making waves. Every gravitational wave detected by LIGO, Virgo, and Kegra falls within a frequency band roughly spanning 10 to 2000 Hz. This range is set by the physical length of the interferometer arms, the mirror suspensions, and the fundamental quantum shot noise of the laser. It is a narrow window. Pulsar timing arrays cover nanohertz frequencies, corresponding to orbital periods of years. In between, from nanohertz to hertz, lies an entire gravitational spectrum that no operating instrument can measure. Rainer Weiss, Kip Thorne, and Barry Barish, the Nobel laureates whose decades of work produced LIGO, have all noted publicly that the current catalog represents a demographic slice, not a census. The Laser Interferometer Space Antenna, a European Space Agency mission with NASA participation, is designed to open the millihertz band from orbit in the 2030s. The Einstein Telescope, a proposed European ground-based successor, and Cosmic Explorer, a proposed American one, aim to extend sensitivity by an order of magnitude. Continuous gravitational waves from rotating deformed neutron stars have been searched for exhaustively and never detected. Either the deformations are smaller than theory allows, or the instruments are not yet sensitive enough. Bursts from supernovae have never been confirmed. Stochastic backgrounds from inflation, cosmic strings, phase transitions, and unknown physics remain undetected or ambiguous. The known event rate implies a total merger population far larger than what LIGO has observed. Most of the universe's violent gravitational events, at frequencies outside our narrow band, at distances beyond our sensitivity, from sources we may not yet suspect, are passing through your body right now without registering on any instrument ever built. Every ripple we have measured has been extraordinary. Every one has raised more questions than it answered, and they represent, statistically, a fraction of 1% of what is actually happening. The universe is not confused. It is behaving precisely as it always has, indifferent to observers, radiating space-time distortions in every direction across every frequency, most of them beyond our reach. What every anomaly on this list has in common is that the confusion is ours, not the universe. LIGO has confirmed general relativity to a precision Einstein himself would have found unimaginable, and in doing so, it has revealed how much of the cosmos remains outside the small window we have learned to listen through. Every detection is a reminder that the silence between events is not empty. It is only unmeasured. If you want to see more videos like this, click the video on screen now.